Welcome everyone to the second day of this workshop. The number of participants is increasing, is 75, so I think we could start. One very quick thing to say. We have 3 presenters for the first part of this session, and we have at the moment 6 contributions for the discussion. So we have a small time and a lot of things to say, so I will be very quick in this introduction. Recall that the spirit of this workshop is to be very informal, so you can interrupt, you can discuss with the presenter anytime you need. And let's see what happens during the discussion after the experience of yesterday that was very animated. The contributions were very spontaneous, so I hope this is going to be the same. So I propose that, Greg, if you want, you can share your screen and start your presentation. I will take the time, but just to have an idea of how much time we take. Thanks.
All right.
Yes.
So, should I get started?
Sure, please.
Okay, so thanks to the organizers for inviting me to talk, and also to, for a nice session, for a nice workshop. I was asked to speak on rupture propagation experiments and their relation to mechanical work and fracture energy. So that's what I'll do. And basically a rupture propagation experiment is one where you can observe maybe like the initiation of some seismic slip and some rupture propagation all within a sample. So to do that, well, you have to have a big sample. And basically the sample has to be big enough that it's larger than some critical nucleation dimension. We can call it LC or H star, or Pablo Ampuero yesterday was talking about LB and L infinity. Basically, there's some critical, weakening, some critical slip distance where if you have a small slipping region, it's too stiff. And if you get a larger region, it becomes more compliant and eventually it can go unstable. So to do this, this critical length scale is about 1 meter in rock at sort of 5 MPa stress levels. It's smaller in plastic. So to do this, you either need a super big rock or a reasonably big piece of plastic. And here's some examples of different experiments that I have found. I tried to include a pretty good representation of big rocks up at the top and plastic sheets sort of on the bottom from around the world where these rupture propagation experiments have been made. The oldest rupture propagation experiment I'm aware of is Johnson and Schultz, 1976. So basically, how do you measure the rupture propagation? Well, the most common way is to put a bunch of strain gauges down. And so you have measurements of strain as a function of time, but at many different locations. And some of the nicest observations I'm aware of are from NIED Japan, where they have a lot of strain gauges, and you can really see the propagation of fronts that are moving in space-time. So here time is on the x-axis. It's strain, but it's plotted as a function of space on the y-axis. So each individual trace is a gauge that's offset going down the length of a 1.5 meter fault. And yesterday Zev pointed out that they have experiments where you can actually see a rupture fronts on a rotary shear apparatus. They're using plastic samples, so they're able to see rupture fronts on a rotary apparatus. If we take a look at the NID results here, I just want to point out some observations that you see from these types of experiments. First of all, you can see it kind of starts right around here. The first rapid stress changes occur here, and this is where sort of the nucleation is occurring. And you can see it's a more gradual stress change right where the slip is beginning. It's a slower slip. And then as you move out from the nucleation region, you see a stress increase, which is the stress increase ahead of a propagating rupture front or ahead of the crack tip. And you can start to track the propagation velocity by tracking features that are observed on multiple nearby stations. And then in this case, so you can sort of see that the rupture front accelerates, it decelerates again, And then when it hits the end of the sample, you can see a back propagating rupture, actually multiple back propagating ruptures. So these things can get very complicated. Here's some sort of classic observations from USGS and Menlo Park. This is a Kubo and Dietrich. And you sort of see the same thing. You can see, here's where I've highlighted where the nucleation is occurring. There's some gradual slip, gradual stress changes. And then as you move out, you can see there's the stress increase ahead of the rupture front, and then a more rapid stress drop. Now they're measuring slip with like a little capacitive slip sensor at the same location. So it's tempting to plot that stress change, not as a function of time, but as a function of slip, as a function of displacement. And if you do that, you can get something that looks a bit like a slip weakening relationship that we talked about yesterday. And from that, you can estimate fracture energy, right? Which is the area of this little triangle. Now, strain gauges are not the only way of doing this. There's more recent experiments where you, from Rosakis's lab at Caltech, Rubino et al. Did high-speed digital image correlation where you can get both the slip and the deformation, which can be converted into strain, which can be converted into stress, and do something similar and get some sort of a slip weakening relationship from that as well. Okay, so there's some issues. One is we really want to know what the stresses are on the fault, but our measurements, whether they're digital image correlation or strain, are going to be made slightly off the fault. And this becomes a significant issue when the cohesive zone, or the spatial extent of the region where it drops from say a static coefficient of friction to a dynamic coefficient of friction, when that becomes small, and that happens when the rupture speed becomes fast, or when you have a small critical weakening distance. When that happens, you get some distortion. So this is some pretty nice demonstration by Qiqing Xu. This is from the NIED group, showing that on the fault, you might have this slip weakening relationship. But if you just go a little bit off the fault, say 5 millimeters, it starts to get distorted. And then 20 millimeters off the fault, where they have their strain gauges, you can kind of see these additional wiggles that show up. And that's at a relatively slow propagation velocity. At a faster propagation velocity, those distortions get stronger. And a similar thing is shown here from Dave Kammer, showing when you go further off the fault, it can really dramatically change the wiggles that you would see from these dynamic strain measurements. Now, Jay Feinberg and his group really took advantage of this and made some pioneering studies showing how you can match those wiggles to a model in order to constrain fracture energy. They put little strain rosettes on small plastic samples, and were able to look at the full two-dimensional strain tensor and look at their dynamic oscillation. So this column here is showing a relatively slow rupture front, where the shear stress, which is the middle panels here, it doesn't look that different, right? It kind of goes up and then it goes down as you might expect. But once you get up to very close to the Rayleigh wave velocity, the propagation velocity, you see some pretty significant distortions, but it matches pretty well with the predictions from linear elastic fracture mechanics theory, which was outlined by Dave Kammer yesterday. Here's an example of some measurements that I made at the USGS at Menlo Park, where you've got rupture fronts. This one sort of appears to initiate at one end of the sample. You've got a row of strain gauges going down and back. And what Dave Kammer did is he took these wiggles from these secondary rupture fronts and measured them, basically, and tried to match them to some theoretical wiggle, and found that as that rupture front accelerates, the amplitude of that strain oscillation increases, which is consistent with what you would expect from linear elastic fracture mechanics. And if you plot the rupture speed and the amplitude of stress oscillation, you can kind of constrain fracture energy. And this is sort of similar to what the Feinberg group has done for many studies. So that's sort of some techniques for how these dynamic rupture experiments can be used to gain some insights into fracture energy and slip weakening processes. Now I'm going to go through some common observations. The first is a rougher fault tends to produce a larger D sub C, a more gradual weakening with slip. And so this is an example from Akubo and Dietrich, 1984. There's similar work by Onaka and Shen, basically comparing a rough fault, which is what I showed before, with a smooth fault. So we're looking at 30 grit abrasive compared to, say, 240 grit abrasive. And you can see two main differences. First of all, the nucleation process on the rough fault is much bigger, which is consistent with the larger fracture energy. Whereas on the smooth fault, it seems to just, the dynamic rupture just starts much more abruptly, both constrained in space and also more abruptly in time. And the second thing you can see is that it looks like it kind of weakens, or at least the strain is dropping from a initial level down to a residual level over a longer time than on the rough fault than it is on the smooth fault. And because the slip is kind of similar, it's also slipping. It's weakening at less slip. So that's the effect of fault roughness. The other effect is normal stress. It's been widely shown that higher normal stress tends to increase fracture energy, not because it increases the slip weakening distance, but because it increases the difference between a peak strength and a residual strength. So you squeeze those, fault sides together higher, and the contacts get a little bit bigger. This is Dietrich and Kilgore directly imaging the micron scale contacts that compose a frictional interface. And you can see with increased normal stress, these green patches, you get bigger, potentially stronger contacts, and also a larger number of contacts. And so, back at Akubo and Dietrich had, increase in apparent fracture energy with increasing normal stress. The same has been seen with plastic samples, Bayard et al. From the Feinberg group, as well as with lubricated. And then I also want to show some examples from my lab. Basically, we measured the number of grooves in the sample and found that increases with normal stress as well. So here's what some of these big rock samples might look like. These are the 3-meter blocks at Cornell before we did any experiments on them. And then after we do some experiments, you can see there's a lot of sort of scratches and wear products that have been made. And I've zoomed in on one of these grooves here. And there's a lot more wear right at the sample ends than there is in the center. And so what we did is we mapped these, we measured the number of smears and grooves, and we found that at the ends where the normal stress is higher, we get a lot more grooves, consistent with this idea of higher fracture energy at higher normal stress. And this is the same sort of process shown on the Gabbro samples at the NIED group. Because the Gabbro is black, you can see it a lot better. You can see how at higher normal stress, which occurs at this one end of the sample, there's a lot more grooves being made. You can see how it's creating gouge by plucking out a grain and grinding it up. And that takes a lot of energy. Okay, the one thing that I haven't really talked about yet is the numbers. Well, what we find is because fracture energy scales with normal stress, I've sort of calibrated these all to a 10 MPa normal stress and found that, so for granite, we're looking at about 1 joule per square meter. A little bit larger for a rougher sample, a little bit smaller for a smoother sample. And that's been confirmed through, okay, so, and then Dave Kammerer looked at secondary rupture fronts. It's a little bit lower maybe, which maybe makes sense that the fracture energy is reduced for a secondary rupture front. There's another study where we tried to constrain fracture energy using rupture termination criterion, found pretty consistent fracture energy of 1 to 3 joules per square meter. Gabbro from the NIED group, about 1 joules per square meter. And then plexiglass or PMMA pretty similar from the Feinberg group, maybe a little bit larger, maybe 2 to 5 joules per square meter. The digital image correlation is showing a little bit larger fracture energy, but sort of an order of magnitude larger. And then the Bayard et al. Study coated the interface with a little bit of oil and was able to increase fracture energy that way. The one outlier here is intact rock, right? So all of this is fracture energy of a pre-existing interface. If you look at intact rock, it's about 1,000 times bigger. And then if we want to scale up these fracture energy estimates to seismogenic depths, we probably want to go up to about 100 MPa, so you can multiply all these by about a factor of 10. So those are sort of the numbers related to these fracture energy estimates that you can get from laboratory experiments of rupture fronts. And that's the end of my talk, and I'd be happy to take questions.
Thank you very much. Thank you.
Yes.
Okay, so let's discussing. We have 5 minutes at least for this commenting on what Greg said. So if you want to say something, you can use, yes, the raise hand tool, the reaction tool. Okay, I think it's Jay. Jay, please.
Yeah, just a quick comment. Beautiful talk, Greg. The outlier that you show isn't actually even an outlier, because if you take the real contact area and normalize it by, it's probably about 1% to 0.1% of the contact area, you'll get the intact rock strengths. So it's not even an outlier. It's basically the same thing. The same works for plexiglass.
You're saying that the intact rock essentially has a full contact?
Exactly. So if you normalize the real area of contact to make it into a full contact, you'll get the same numbers more or less.
The one thing that makes sense. The one thing I would say is that you also get an increase in the intact rock fracture energy with increasing normal stress as well, right? So not sure exactly how that fits in, but well, yeah.
You win some, you lose some. What can I say?
Yeah.
All right. There is a contribution from the chat. So yes, I agree. That was a very informative. Thank you, Greg. We have a comment from Omid. Please go ahead.
Yeah, thank you, Greg, for this nice talk. We are all aware of the stiffness of the system and how this will affect the result. I was wondering if you have tried to also normalize this fracture energy by considering the stiffness of the system and how that will affect the results.
Right, great question. So I guess the way I would answer this is that in these rupture propagation experiments, the physics and the mechanics that we observe is dependent on the material, and it's not necessarily dependent on the stiffness of the machine. So that's what separates this between like a stick-slip experiment, where you have a critical stiffness, and that's the transition between sort of this quadrant of the diagram to this quadrant. In that case, instability and the dynamics of stick-slip can be dependent on the compliance or the stiffness of the machine. But when you have a large sample, the machine is not necessarily controlling anything other than applying your forces. The instabilities that develop are developing due to the compliance of the material. And so the reason that it's a little bit easier to do these types of experiments on plastic than granite is because the plastic is more compliant. So you can get this instability to develop at a smaller length scale.
Thank you.
Okay, Georg, please.
So great talk. Thanks, Greg. So the numbers that you showed were really small, and they were of the order of, these mode 1 fracture experiments that were done in the early days of just a few joule per square meter. Now, for the experiments that were performed under pressure, triaxial tests, the numbers are significantly higher. And I may have missed Jay's comment, but I don't really know how you would compare that. Also, when you perform tests to measure K1C, like these ISRM chevron notch tests, you end up with numbers that are significantly higher, of the order of 100 joule per square meter.
Well, yeah, okay, great. So, so I'm putting this 1 to 2 kilojoules per square meter down for the Wong et al. Study. This is a very low normal stress number. You got to go up at least a factor of 10, maybe 10 per square meter to get up when you're in the 100 MPa range, right? And those experiments were done at high stress. I'm not aware of experiments that use, maybe Pasileg has some data that he can share with us, that try and constrain fracture energy using rupture fronts that are observed at high confining pressure, because almost all these experiments are done in the 5 or 10 MPa range, right?
Okay, maybe Francois has some contribution for the discussion. I think maybe we can postpone this discussion at the end of the session, the first session. We have some time, very tiny time, for another comment by Dimitri Garagash, please. You want to contribute?
Yeah, thanks, Greg. Very insightful. I was just wondering, in view of the discussion and talks that we had yesterday, in terms of the apparent, well, not just apparent in the lab as well, the dependence of fracture energy on the event slip, would it make sense to put some sort of acknowledgement of what is the scale of slip in these experiments, where the fracture energy being inferred in the table that you give, I guess?
Yeah.
Or if you have a comment.
Yeah. That's a great point. I didn't really mention it, right? But these are all experiments where the slips are on the order of microns, right? So we're never getting slips up to 1 millimeter. So all of this weakening, all the fracture energy that we're measuring is occurring under, maybe 10 times the d sub c or something, maybe 100 microns, but not more than that. So it's quite different from what you might infer from a rotary shear experiment, for example.
Okay, thanks. So maybe would it make sense if we do something on a larger machine with smaller d sub c, or larger sample, that we could possibly observe in actual spontaneous experimental dynamic rupture, we could observe the continuous weakening and continuous increase of fracture or breakdown work with slip, I guess. What do you think?
Yeah, so I've been thinking about this actually a lot over the last day, mostly because of Zev's point yesterday, right? That trying to separate out, and also Dave Cameron's point, trying to separate out like processes that are happening right at the front of a propagating rupture versus processes that are happening more in the wake of the rupture. That so I think, what we would love to have is a really, really big rock, 10 meters, 100 meters or something like that, where that is suitably rough, and where you can actually get a dynamic instability to develop. Because I think you really need to have that roughness to sort of see how this is going to scale, because all of these lab samples, you can see, are way smoother than you would expect in natural faults. But you also need to have a dynamic instability that's going to load the sample very rapidly with very high slip accelerations. And the slip accelerations that we can observe in these dynamic rupture experiments are kilometers per second squared, tens of kilometers per second squared. This is something that's not yet achievable, even with the fastest high-speed rotary machine. So we may be looking at differences in terms of slip accelerations as well.
Thank you.
Thanks, everyone. It was really interesting. Thanks, Greg, for your contribution. I think that we should move on. And Paul, I take notes of your raised hand. Maybe we can postpone your question for later. And I also am reading some question in the chat, so we can postpone also this discussion if you all agree. And I would like to invite the next speaker, which is Stefan.
Hi, can you hear me?
I can, we can.
Okay, great. I'm never sure. I'm going to share my screen, and you'll notice I may have, okay, I hope you're seeing my screen now.
Yes, we see your slides.
Okay, let's get started then. So first, well, high velocity friction experiments, that's what I was asked to talk about. And obviously there's a large number of people who have contributed to this field in the past few years. I was lucky to work with a few of them. And let me take this opportunity also to thank you for organizing this wonderful workshop. I had never had so much fun for quite a while right now. And so next slide is, yes, there was a 25th anniversary of high velocity friction experiments, I guess 1 year ago. So this talk is going to be, well, trying to compress 26 years of experiments in 15 minutes. So that's less than 1 minute per year. It's going to be difficult. I hope you'll forgive me. So going back again to the title of the talk, if I sort of destructure the title and try to define term by term, I hope that we all know what is an experiment, but maybe it's not that clear what is high velocity in terms of earthquakes and what is friction. And so that's one of the things I'm going to try to define in terms of the discussion that happened also yesterday. And the other things I want to talk about also is to describe the different setups and the different materials and the variable outcomes as a consequence of different conditions and materials that we can apply to the experiments, the scaling aspects and the implications for earthquakes and fracture energy, which is a part I added since I heard the discussion yesterday. So I'm at an advantage here. So let's go forward. So what's the slip velocity in earthquakes? Well, we got a big range because we go from tectonic plate motion, which is a fraction of a nanometer per second, the slow slip experiments in the lab, a few microns per second. Then there's a whole range of slow earthquakes. And in terms of seismic rates, it's difficult to measure the slip velocity. Maybe it's easier to measure the stress drop. And if you throw in parameters together and try to get something that makes sense dimensionally, we put in the stress drop, the wave velocity, and the shear modulus, and plug in the numbers which are representative of earth crust, for example, we get something that's of the order of 1 meter per second. But that's a very rough estimate. The proper way of doing this, let's say theoretically, it's to write down the representation theorem, which I believe the first one who did that were Koshar and Madariaga, and then Rice also developed that further. So basically you get the stress drop during the earthquake, the change of stress during the earthquake, the dynamic change of stress, not the stress drop, which is the contribution of two terms. And you can reverse that and get the velocity out of it. So there's a contribution of the stress change locally, right where the rupture is, where the point that is considered is. And then the incoming term, which is the remote stress transfer from the rest of the fault. And you can write that as an integral form over time and over the fault. And the important part here is that, well, there's a very complicated kernel here, but this is slip on the fault. And there's the second derivative on the fault. So basically this term here, which is the transfer stress, is sensitive to the curvature of slip on the fault, the second derivative of slip on the fault. And so if I write again this a little simpler way, I have the sum of two stress terms here, times the dimensional coefficient here. The second one is the incoming from the stress transfer, and it's sensitive to the curvature of slip again. And we know that close to the crack tip, when it starts to accelerate, we have a very, very strong curvature of slip. Therefore, we have a very, very high stress concentration. And therefore, because of what is written here, velocity is proportional to the sum of these two stresses, a very, very high global stress, net stress concentration in the crack tip will have as a consequence a very high velocity peak. Maybe now those who know me guess where I'm going at. High velocity, so we live in a world of velocity weakening since we started doing high velocity experiments 26 years ago. Therefore, high velocity in the vicinity of the rupture tip means fast weakening in the vicinity of the rupture tip. Oops, I'm going a little too fast here. Fast weakening in the vicinity of the rupture tip means a very, very, very fast drop in stress. And if the rupture is propagating close to the Rayleigh wave velocity, you have the Lorentz contraction. And Juan Pablo, luckily yesterday, talked about Joe Andrews, and Joe Andrews was one of the person looking into this. The rupture front, the process zone in terms of the zone where the friction is dropping, rapidly shrinks to zero when you approach the Rayleigh wave velocity. So without necessity of invoking anything else than friction here, we can reduce the, let's say, the high intense weakening at the fracture tip just by having a fracture accelerating, just by invoking velocity weakening essentially, and this very strong stress concentration. So I'm going to try to convince you that part of the discussion that was started yesterday in terms of the difference between fracture energy close to the crack tip, breakdown work, and a gradual weakening that happens after a little later during the rupture and probably during the whole slip for earthquakes. Well, I think that everything is compatible, and from my point of view, it can be explained in terms of friction, except that close to the crack tip, the friction evolution is extremely fast due to this high load of transient stress. Okay, so let's see where I'm going with this. So now we can fill in this with 1 meter per second. We have a huge range of velocities here, more than 10 orders of magnitude. You can understand it's now difficult to model earthquakes, but this is probably much higher than 1 meter per second close to the crack tip. Now, in terms of what we do experimentally, there's a big variety because we first have both igneous or sedimentary rocks, okay? And then we have either cohesive rocks or gouge. And if you combine all these, let's say, end members like granite and basalt for the crust, and then sedimentary rocks, which could be calcite, limestone, marble, or clays, and include phyllosilicates, in particular smectite, which is extremely weak. Well, you have a large combination of experiments possible here, and then you can add fluid or remove fluid, change the pressure, change the velocity. Well, we barely started to scratch the surface of all these possible combinations. Now, in terms of experimental setups, I think we can look at both what, in my opinion, what Greg showed earlier, and the more traditional imposed slip velocity experiment can be used to measure friction. So in one case, as Greg was explaining, this slip is spontaneous and you have to use strain gauges to measure the change of stress, and you can sort of infer also the slip and the slip velocity, and you relate the two, you get a friction weakening law from those experiments. It's a bit more difficult, of course, than just imposing slip directly and measuring the resistance, which is on the left-hand column here. And the types of apparatus we use for that normally are rotary shear, but also some people have been using an impact bar or a triax or biaxial with a fast piston. I'm going to talk a bit more about this later on. Okay, so the difference between the imposed slip, of course, and the spontaneous slip is that in the spontaneous slip, you have the propagating tip. Therefore, you have this very strong stress concentration, which induces a very strong velocity, slip velocity peak close to the rupture. This velocity peak is very difficult to reproduce in the imposed slip apparatus because you cannot very easily impose a very fast acceleration. Although recently, Harbord and Nicolas have tried to impose the shape of a pulse, but it's nowhere near the acceleration that you would get into a natural propagating pulse. So these are the main difference as a consequence of the two setups, in one case spontaneous, in the other case imposed. And these may result in different estimates of maybe fracture energy and surely sleep weakening distance. In the process of doing this, I learned how to produce actual slides rather than TikTok movies. And so let's go on like this. So imposed velocity, again, there are different types of apparatus, and the impact bar is probably the one that combines the fastest loading and the highest normal stress. There are some intermediate apparatus now that's been recently built by Violay and her group at EPFL, which is capable of imposing pretty reasonably fast velocities and high stresses in a confined ambient. And then there's the rotary, which is the classic go-to apparatus, and there's quite a few of them around the world right now. Then there's the spontaneous experiments, again, so some done with the biaxial press. Many of them are done on plastic materials. And then there's the direct shear blocks on granite, as McLaskey just talked about. And then you can do the same also inside the triaxial press by loading up to stick slip a pre-cut sample, like in the work of Pasleg et al. Now, first, let's look at the impact bar results. This is amazing because you have an extremely fast drop of friction here in red. The result of this, well, is about 1 micron of sleep weakening distance, or equivalent sleep weakening distance. I'm just want to make sure I'm aware of time here. The loading, the sleep velocity here is of the order of 15 meters per second on average during the loading phase, very fast. And the normal stress is 247 MPAs. So this is really on the high range. And my argument is that this explains why the DC is so small. However, it's still compatible with possibly the meter scale sleep weakening distance that's observed in some of the rotary shear experiments. And the reason is because the combination of normal stress and velocity, the product of these two things, is much smaller for rotary shear experiments. Now, what are the main results over the past few years in rotary shear? Well, you probably know this graphic where we illustrate that when you reach about 1 centimeter or plus 1 centimeter per second or faster sleep velocity, there's a profound drop of the friction coefficient, and different types of rocks probably weaken due to different mechanisms. So we have melt lubrication in red, we have flash heating in blue here, we have decarbonation in green. We have different types of mechanism, but they all point to the same idea that when you reach a fraction of a meter per second, everything becomes weak. Now, this is as a function of power rather than velocity, which is the product of stress and sleep velocity. And stress, at least in the initial part of rupture, is proportional to normal stress. Shear stress is proportional to normal stress. And so if I represent some of these results, this is just for frictional melt, but it works in general. If you plot the weakening distance as a function of not exactly the power rate here, but the normal stress times the velocity, the square root of velocity in this case, you get a in log-log, you get a linear drop like this when this sort of proxy for power rate increases. The weakening time is actually decreasing linearly, log-linearly with the power rate, but the sleep distance is decreasing like sigma times v square root. And if you were to extrapolate this regime measured in rotary shear experiments to the higher power rates here, you'd understand that continuing to go log linearly down, you would quickly reach the millimeter scale, and then probably the micron scale, which is for DC what is observed in the impact bar experiments. Now, the other issue with rotary shear experiments, or the other observation rather than issue, is that there is an extremely fast drop at the start, but then it continues to weak for a very long time. So it's very difficult to fit this with an exponential, which means it's difficult to find a characteristic length, especially when you plot in log-log, you realize that this weakening phase looks more like a power law, and power law says lack of characteristic dimension, and probably presence of some self-similar process at all scales. So if you were to stop the rupture earlier or later, you would have an apparent slip weakening distance which increases with slip. So the other consequence is the very strong weakening during that phase where you reach a few centimeters up to 1 meter per second, means that the equivalent stiffness of the fault or experimental fault would increase abruptly, because the derivative of the steady state friction has a strong weakening. Therefore, you could go from a stage where the fault is in a metastable state, and it's get pushed over that stable state where maybe it's velocity hardening, therefore it's stable, kicked into this regime, and have a very strongly accelerating and strongly unstable phase until it reaches the high velocity. And this is the reason why in this regime of a few centimeters per second, let's say intermediate velocity, or a few tens of millimeters per second, it's extremely difficult to perform laboratory experiments, because we incur in very strong vibration of the machine. Now, the good news, so I've tried to figure out what's the stiffness of different machines. The rotary is about 52 kilonewton per millimeter. The triacs in general are a little higher than that, but this new machine that's again at EPFL now is almost 10 times more. So it's exactly designed to work in that intermediate regime. And so I'm curious to see the results from that. Now, in terms of the biaxial and triaxial results, these are a little similar to the impact bar results in terms that the slip weakening distance is extremely short, and the apparent fracture energy, if you integrate the breakdown curve as a function of slip, you get an apparent energy, and you can plot this, and it's quite small. You can plot this together as Pasleg has been doing here with earthquake results, and they seem to sort of increase with the slip, both in the lab and in the earthquakes. And if I take this a little further, okay, several persons among which I am have plotted this type of curve, trying to reconcile lab experiments and seismic apparent measure of fracture energy. And what we see is this log linear trend again, where fracture energy increases log linearly with slip. However, for the rotary shear experiments, there seems to reach a saturation, because even if it weakens for a long time, after a while, it does stop weakening. It reaches a sort of steady state. The steady state is after several meters of slip. And earthquakes seem to continue to have an increasing apparent fracture energy. This is another, let's say, iteration of this thing by Saylor et al. And in this case, they were able to separate different types of lithologies. And for each lithology, it's a little more clear that we're on this log linear trend. And you can add also natural earthquakes and try to find out if the trench material corresponds to the experimental and to the earthquake fracture energy here, which is interesting. Now, in terms of physical processes, what happens? Why does it weaken so fast? So you know about flash weakening. Flash weakening is a very powerful process, but we don't know the macro scale inducing flash weakening. We just know that the asperities becomes hot and the weakening, but what is the particular weakening mechanism inside the asperity? That's a research matter, I would say. Now, mechanisms that may happen are decomposition aided, weakening or frictional melting of the asperities, and we may have fluid pressurization on a local scale also. The carbonation is one example of the composition, which happens both in calcite and dolomite. And then the asperities may start to flow under either dislocation or diffusion creep, which are usually studied at very, very low strain rates, but they can be effective also in a sort of superplastic way at high deformation rate. There's also pressure solutions, silica gel, and other mechanisms, but many of these involve a temperature change. And the temperature rise is enhanced by frictional power. Let's say the way of reaching a high temperature on the fault or on the asperity is to have a high frictional power or a high combination of normal stress and slip velocity. So now we're sort of closing the loop. We go back to the beginning of this talk where I was arguing that by increasing the power rate, we were able to weaken the fault faster, and therefore close to the high stress concentration, we had a very high frictional power and very high velocity, which induced the weakening. So in terms of mechanisms, also interestingly, we can use, oops, I'm going back, a flow law, a classic flow law with a power dependence on the stress, a power dependence on the particle size, and an exponential with an activation energy. If we take the log of this equation, which gives a flow rate here, we can write that the log of the stress is proportional to the sum of two terms, essentially. One is the inverse temperature times a constant, and the other one is a logarithmic dependence on flow rates. And so Pozzi and authors have been measuring these quantities in the lab experiments and plotting them in log-log scale, and they find that effectively you have this log linear fit here if you plot inverse temperature as a function of the log of the shear stress measured during this high speed experiment. And they did this for a variety of materials here, and they all seem to involve this kind of plasticity law, which is enhanced by high temperatures. These experiments are all done with gouges, and they're measured at the steady state regime. So we have a continuous layer rather than, let's say, asperities in contact. Now, because we have multiple mechanisms, we may assume that in a given circumstance or in a given phase of rupture, one mechanism may be more efficient than another mechanism. For example, at the beginning, the temperature, the bulk temperature is relatively low, but the concentrated temperatures on the asperities may favor frictional heating or flash heating. But as you go on, you start to have maybe bulk melting or the creation of a pervasive zone, shear zone, where you have a flow law. And then if that mechanism is more efficient, you're going to switch over to that mechanism. And so Cornelio and co-authors have been looking into this and trying to find what is the most favorable mechanism as slip progresses on the fault. And they find the switchover from flash weakening to another mechanism at different lengths depending on the type of rock and depending on the depth. And so this shows somehow that you have a never-ending cascade of weakening processes as the fracture goes on, and not a single mechanism can be invoked, but more to the point, as one mechanism maybe saturates, another one is ready to kick in, which allows you to have this weakening, which is very, very fast at the beginning, but will continue to go on for a large time, okay? What I forgot to say also in terms of fracture energy, when it saturates, it is probably because we have to invoke off-fault damage, and that connects a little bit to the talk that Juan Pablo gave us yesterday. Okay, I think I'm done with the time allotted. Is that so, Elena?
Yeah, a little bit. So we are out of time for question in theory, but we can maybe save sometimes for one question and then postpone everything else to the discussion.
maybe not a problem to have a few questions. We got plenty of time.
Nice. And Stefan, that was amazing. The first part of your presentation on TikTok was really nice.
Ah, the TikTok, yes.
Thank you. So questions. Please, the first one.
Yeah, fabulous talk, really interesting. You mentioned about how you get weakening with temperature and how you get these very long slip weakening distance in rotary. And I wondered if you could just say a little bit about the differences between, let's say, the roughness based and critical friction distance, the based D sub C versus a thermal D sub C associated with, let's say, heating. And I'm thinking in particular because if you've got a bare surface, then the heating can be very direct and important. But if you've got a zone over which slip is being accommodated, a gouge zone, then it might not be, you might not get as much temperature. So.
Yes. Okay, thanks. Very interesting question. So the thing is, in the rotary experiment, when you work on gouges, you do add an initial strengthening phase. So it doesn't weaken from the very start of the experiment. So this has been shown, I think, by Stephen Smith in the early 2010s first, and then other people too. But systematically, when you start to work on a gouge, the weakening will take longer to happen and will be preceded by a slip hardening phase, which can be quite long. And the reason is we believe that you have to reach a sort of shear localization, which will take time to be constructed inside the gouge. And so you have the creation of many shear planes, which are misoriented, which are misaligned, and gradually they sort of collapse onto each other and create a single layer of about, I would say, 30 microns thickness. That's what we see in calcite. And once it's down to this thickness, then you're able to efficiently produce a very high temperature and the weakening kicks in.
Okay, thank you.
You're welcome.
Massimo.
Yeah, Stefan, I would like to ask you if you can comment on two issues that you touched in your presentation. The first one, if in your experiments, especially with the rotary, you can do both imposing the load and imposing the slip velocity. Since you are correctly pointing out the high level of peak slip velocity that you can reach in the rotary when you have slip of order of 6 meters. So I wonder if you can shed light on, point out which are the implications on the pulse-like that Pablo yesterday presented. And the second question concerns the fact that you have in your experiments, you also generate these gauge. So you separate, you impose these huge localization since the beginning, and therefore which could be the implications for the scale dependence of fracture energy that you have shown in the scaling.
Okay, that's quite a long question, so sorry, I'm a bit confused. So the first part of the question, so yeah, so I think if I can answer your question, it was about the peak velocity reached in rotary experiment.
If you see differences when you impose the load or you impose the slip velocity. So do you still see this continuous decreasing of shear stress with slip, both when you impose the load and when you impose the slip velocity?
Yes, of course. When you impose the load, it's more difficult to control, and you sort of have stick slip events, which can be quite small. And eventually, when they get big enough, it continues to slip, and then it will become weaker in the same way as when you impose velocity. So I don't think there's a fundamental difference in the friction, whether you impose this load or you impose the velocity. Now, interestingly, I think Zev mentioned yesterday that even in rotary shear experiment, you can generate a rupture front, right? It's because you have an instability that starts at one point of the sample and start running around. So, but I think that's a local process, and what is measured usually in rotary shear experiments is the average friction on the whole sample, unless you start putting strange gauges on it. Now, sorry, the second part of the question, Massimo.
The second part concerns the continuous decrease of slip, because here we are discussing and we are focusing on the role of shear stress evolution as a function of slip, which is a way to formulate the constitutive law. Yesterday, Valer showed us this suggestion of this continuous slip proposing thermal pressurization, but you have shown today that there are laboratory evidence that this is the case. And therefore, if this is due to the velocity or temperature control on this.
Okay.
If there is a competition between the velocity control and the temperature control, because you can express this behavior with both parameters.
But I think, Massimo, that for me, the velocity is related to the temperature, because if you start to accelerate the slip, the temperature will go up because the power is getting higher. So you produce more heat in a little time. If the time is short enough, heat diffusion is not efficient, and therefore the heat will remain on the fault. So I think that velocity and temperatures are really related to each other in this case. Now, temperature, of course, then can trigger a number of things, including fluid pressurization. You can, I think Dimitri is with us today. I'm not sure Nicola is, but they proposed in a paper a sort of combined mechanism with at different scales in which also fluid pressurization was involved. But all of these were based on temperature, which is also, again, once more, related to the slip velocity, which is the frictional power, which generates frictional power, which is the heat generating mechanism. I hope I answered to your question. Sorry.
Yes.
Confused.
Okay, thank you very much. I think we can discuss a little bit more in the end of the presentation time. There is a lot of discussion going on the chat, so I took notes and we will take over during the discussion section. So next, Chris. Please, Chris, if you want to share your screen.
Okay, I am doing it. And yeah, how's that look? Do you see my slide?
Yes.
Okay, fabulous. I have to start by saying that it's unusual for me because normal policy for me is that any meeting that I have anything to do with organizing, I won't give a talk. I don't know how I'm giving a talk in this meeting, except for the fact that I didn't say no fast enough, maybe when Massimo invited me, asked me to. So here I am. Fabulous talks by Greg and Stefan, and also really interesting talks yesterday. So what I decided to do was to really make some comments try to make some comments about the talks from yesterday and to bring a few things in that have just been on my mind. So in particular, in connection with the project that I'm running here in Rome, that's called TECTONIC, and it stands for all this stuff about the physics of earthquake faulting. So I was assigned this as a title, low velocity friction experiments, and I added the idea that to think about the onset of frictional instability for the spectrum of behaviors that are occurring. So I think this will follow on quite nicely with especially things that Stefan just said for us. I really have just kind of 2 or 3 points I want to make, and so hopefully I can do it fast enough to encourage discussion, not just about this talk, but in general. And yeah, this is the first one of them, is an idea about the fact that the fault zone width is a function of slip velocity. And I know it's true in our experiments. Of course, I can't guarantee it's true in nature, but I know it's true in our experiments from some things that I'll cover. And so I guess I'd like to bring up the possibility that this is a nice little slide that was given by Dan Faulkner yesterday, and about the idea between on-fault and off-fault processes. And I suppose for me, it feels like maybe we should be generalizing that idea, that on-fault and off-fault might be a function of strain rate in an accelerated rupture. And so, you know, I'm simply showing us a sketch, I guess, from Dan's slide yesterday, and then some microscopic images of our fault zones in the lab to indicate that, you know, even in the lab where you have a fault zone, a gouge zone that's a few millimeters thick, it's not, the strain is not pervasive in that few millimeters, right? It's localized, and the localization dimension is a function of slip velocity in a way that I'll show you. So let's go on. I suppose I want to make 3 points, and I'm just making them on this slide right here to, I'll go through it to explain a little bit, but hopefully this will generate some discussion, because the fault zone width is a function of slip velocity, and therefore the critical slip distance, the friction weakening distance, is a function of slip velocity, independent of the sorts of things that Stefan was just talking about with heat, which are obviously important. But because of that, the fracture energy is a function of slip velocity, because it is clearly a function of d sub c. So I thought I'd start with that and then kind of show some things that go along with it. This is a slide from Sam Haynes's work that just makes the point that in our experiments, the shear fabric develops progressively. Lots of people have shown this. It's a slide from Sam put together from experiments run out to different shear strains, engineering shear strains here, and you can see different developments of shear localization. And what I want to do is talk a little bit about the way we can measure the shear localization dimension in our experiments. And I pulled two things from previous works of our own that were easy for me to get a hold of, not to indicate that we're by any means the only people who've done this. But on the right-hand side is a compilation of critical slip distance measurements as a function of shear strain for some different layer thicknesses and particle size distributions. And what we were able to show was that you can't explain this variation in the critical slip distance by comminution or anything else, because the differences in the particle sizes that we started with were huge compared to the differences in d sub c as a function of shear strain. So this is an argument that d sub c is getting smaller as a function of shear strain because of localization, right? So just an idea that this is giving us a way to measure the active fault zone. And on the left-hand side, some work from Andy Rathbun, where he did some stress steps. So these are shear stress steps to try to measure the dilation associated with them, and watched how that changed as a function of shear strain. So for me, these are both indications that the active fault zone width can be measured and decreases systematically as a function of shear strain. The other thing that's relevant to this is just some direct measurements of d sub c as a function of velocity that Karen Mayer did a while ago. And they show a simple relationship here. I don't guarantee, in fact, I doubt that this is true for every kind of material. This was true for some granular quartz material, and there was a clear increase in the critical slip distance as a function of velocity. So I should have said that actually in my first slide, is that there are some cases where the critical slip distance will increase with velocity, and I doubt that that's generally true for every single kind of material. So I also pulled a slide from Pablo Ampuero's talk, which I thought was really interesting, where he started to talk about the off-fault, the inelastic zone, and how that inelastic zone grows in proportional to rupture size. So I feel like all I'm doing is adding to that by saying that what we call on-fault and off-fault, and what we, in this case, it's called off-fault plasticity, could involve things that are just outside the zone of active shear within a zone of granular material, within the shear zone itself, within a zone that might have quite a low, let's say, shear wave speed relative to the real country rock that might be a long way outside the fault zone. And so I thought I wanted to add a few more things about that related to the spectrum of fault slip modes, because I think when you look at the transitions on the left-hand side, these are a series of experiments from Marco Scuderi's work. These are a series of experiments of different normal stresses there's a step right across the stability boundary. So at 13 megapascals, you just get stable sliding. At 13.5, you get something that's basically stable sliding, and these tiny little things might be something. And then as you go above 14 megapascals, you start to get more and more dynamic instability. Some of these are slow, some of these are complicated, but I think and I'll show you an explanation for why this occurs that connects in with this idea that the critical slip distance increases with velocity. So, in these experiments, you can carefully measure what happens with the fault slip velocity during the instability. These are slow instabilities, right? So this instability is occurring over a big fraction of a second, and the peak slip velocity is only reaching a few tens of microns per second. This is a very slow slip event, but it's dynamic in the lab, right? It's quasi-dynamic. When you look at a range of things, that's the same data set from Marco, and this is some data from John Lehman, a very similar set of conditions. And I just want to draw attention to the idea that these low normal stress instabilities are occurring with very small particle peak slip velocities. And you can look at the complete transition from basically stable sliding through slow slip and fast slip that can be reproduced in the lab. And then you can ask the question of like, well, can this be produced by the same friction law? What does it mean in terms of why this slow slip occurs? What controls the slip velocity in these cases? And I think we know, adding to that some other data showing this nice relationship between stress drop and peak slip velocity. So this is also seen in seismic events, and it's sort of obvious in some sense that the very slowest earthquakes have tiny stress drops. And you can see that relationship in the lab as well, right? So the stress drop goes on basically slightly, almost linearly with the peak slip velocity. The question, why does that happen? Well, here's one explanation for what's going on with it. This is just a simplistic explanation that's based on the critical slip distance and critical stiffness idea that Greg McLaskey mentioned a few minutes ago. It's some experimental data from John Lehman. It simply shows what happens when you're near the stability boundary and you change the velocity. So this is a section at 10 microns per second. You can see these are unstable slip events. At 30 microns per second, you get smaller instabilities. And at 110 microns per second, you get basically stable sliding with some noise, right? So it's consistent with this kind of idea. If you look at stiffness as a function of velocity and you put the critical stiffness on here, right? So at a given velocity, you can say, oh yeah, when I have a very stiff system, very small, very stiff system, or a very large elastic modulus material, for the way that Greg McLaskey talked about it, I'll get stable sliding. And as I go to lower and lower stiffness, I'll transition at some point through the instability. Well, what these data show is that the stiffness curve must look something like this. This critical stiffness actually decreases with velocity in a way so that if you're near the stability boundary, when you go to higher velocity, you go into stable sliding. You can ask the question of like, how does that work? What makes it happen? And it's also connected to some like systematic data that show what happens here, where if you look at stress drops as a function of slip velocity for a bunch of experiments, like what I just showed you, you go across the stability boundary and you get basically stable sliding at different velocities depending upon the normal stress in a way that is completely consistent with our ideas about the critical stiffness. So we can see that this happens, and we can ask, what goes on with it. And part of it is the increase in d sub c with velocity that I showed you from Karen Mayer's work. And another part of it might relate to this thing that Pablo Pereira showed us yesterday, so-called V-shaped rate and state laws. Now, he showed a curve that looks like this. And I'd like to just point out that our data are very similar if I just replace the y-axis here with basically the rate state friction parameter A minus B. And what you can see from some modeling studies is that you don't even need to cross the boundary. You don't need to go from velocity weakening to velocity strengthening to make this happen. You simply need to have a reduction in the amount of velocity weakening as you go faster to produce this kind of slow slip behavior. So I think it's consistent with a bunch of things. And I'll just come back to the main point. This is the last slide I wanted to show. Come back to the main point I started with, which is that from our experiments, it looks like the fault zone width is a function of slip velocity, at least in some cases. It's consistent with an idea that is simplified in this diagram, but that even in a fault zone of finite thickness, the strain is accommodated within localized zones that are a function of slip velocity and shear strain. And so because of the fact that the fault zone width is a function of slip velocity, the critical slip distance is a function of slip velocity, and therefore the fracture energy that you measure and that's important is a function of slip velocity. And I think it explains in our experiments why when you cross this stability boundary, you end up in a situation where the stress drop is essentially zero. And that is because the available energy to drive rupture is so small, and all of the energy is used in accelerating the fault so that there's nothing left to radiate energy from. So, okay, hopefully I've kept us a little bit on time. I will stop there, be happy to answer a few questions, and then I'm really excited about all the people who've talked about contributing something. So I'll stop there.
Thanks, Chris. Thank you very much. Very nice talk. I'm looking at the chat. Okay, no chatting question at the moment, but is Jay with a raised hand, please?
Yeah, just a quick comment, question, something. We all use the D sub C terminology to talk about the slip distance, but I'm not sure that the D sub C in friction experiments is anywhere related to the D sub C that we use in to talk about fracture energy. Typically, it could be, the scale at which a plasticized zone near the crack tip goes away or something, which has very little to do with gouge, with grinding, with anything. I think we're using the same letters, but that doesn't necessarily describe the same thing. Stefan tried to he made a point of relating this rapid velocity weakening to what's going on in the process zone of a fracture, but that isn't necessarily the case either. It's a plausible explanation, but it's not necessarily the only explanation, especially since the rapid velocity weakening that you see in the rotary experiments takes place over very long slip distances, where in the rupture experiments or rapid rupture experiments, the slip distances are very small. So it was just basically a word of caution. I guess we should change our letters or something, so not to confuse ourselves.
Yeah, I guess I couldn't agree more in some ways, because imagining that there's one critical slip distance that applies to all the different cases when you've got thermal processes as well as just simple frictional processes, for sure. I guess I'm just using something that relates to this diagram, the idea about some energy on a diagram of stress drop as a function of slip, and the critical slip distance being the idea that there's some weakening that happens.
Yeah, I'm just as confused as you are, but basically all that this diagram is telling us that there's some scale involved. Yeah. I also thought it was interesting. Yesterday in the chat, there was a bunch of discussion about pulverization and the role of that, and that's part of what motivated me to think about what we know about the critical slip distance as a function of, let's say, strain rate in your experiment. Thank you.
Massimo.
Yeah, I want to follow what Jay just said, because I agree that we need to be careful with the terminology. So yesterday, Pablo showed a relationship between the D sub C from the slip weakening curve and what I call L parameter of rate state friction. the scaling depends on velocity, slip velocity. So, and if you do 2D or 3D dynamic rupture calculation with rate state friction, you can find that this relationship holds. So we did with Andrea Bizzarri this type of simulation back in 2001 and 2002. The issue to me is, and in this case I agree with Jay, is that YL is in any case a length scale parameter in the rate state constitutive formulation. D sub C it is not, because I think that we all agree that D sub C of the slip weakening curve is not a constitutive parameter. And we have several corroborated evidence of this. One over the others is that if we have off-fault damage, you have the scaling of D sub C with the thickness of the fault zone and with the plasticity. So I fully agree with Jay. So we are comparing, and to me, it is also to be understood how much the scaling that we inferred and Pablo yesterday have shown can be extrapolated to a broader physical interpretation and to real fault zones. Perhaps it's just a numerical artifact of using rate state friction in 2D, 3D dynamic calculations.
Yeah, I don't know, good point. I mean, I see Dimitri's got his hand raised, but it'd be interesting to bring Greg McLaskey back into the conversation because, you know, you say D sub C is not a constitutive parameter, and I agree with you, it's going to vary as a function of all these things, but when you go ahead and, you know, make measurements of fracture energy, you're making measurements that depend on the D sub, you know, the details of the way your experiment worked, right?
Yeah, and can I add just one comment to Jay, that moreover, even the definition of the sub C is strictly dependent of the slip weakening law, of the constitutive law that we adopt. Because if we are in the IDA world, on the idanium, virtual material, this sub C is not questionable because we have the constant residual stress. And in this case, everyone is happy. The J integral works, the fracture energy, it is the same computed with the cohesive zone and so on, as David shown yesterday. But as soon as we have completely different shapes of the slip weakening curve, including the continuous weakening that Stefan and Valer yesterday shown, so what is this sub C? It's the same if we measure the minimum stress instead of the residual, or at the dynamic friction for a continuous decreasing. So to me, this is exactly the issue that we need to reconcile to adapt a coherent interpretive framework with the reality, not only with geology, also in the lab.
Yeah, couldn't agree more.
Yes, I totally agree. It's very difficult, but maybe later in the discussion we can also comment on how this could affect the scaling of the energy, because in the end, if you put all the data together from intact rock, stick slip, different loading type, slow earthquakes, fast earthquakes, the scaling seems to suggest that there is something like a good scaling with some different trend. Dimitri was the first in line.
Yeah, thanks. Thanks, Chris. Very interesting talk. I was just listening. Well, I had initially a different question about this relation that you propose in between the D sub C and the slip rate for one. But actually, hearing some comments, I wonder if we can reconcile, you know, all this discussion, whether we have the D sub C and what is D sub C and how do you put it in perspective of continuing weakening processes where essentially the fracture energy never saturates but grows with seismic slip, right? As has been inferred also. So perhaps we should be thinking of a cascade of weakening mechanisms, and perhaps the first one, and it might be related to localization of slip, has a well-defined D sub C or L, so essentially comparable to the thickness of the initially distributed slip zone, right? And then you could talk about the subsequent weakening mechanisms, which may not necessarily have, right, a specific slip scale at which the weakening is saturated, and therefore, so that was just the comment that I thought in spur of the discussion that's going.
Yeah, really good point. I like it. Yeah, I mean, I think for me, if this sketch helps us at all, it maybe just helps us think about it, in a transient sense, the frictional properties of all these contacts are important. The frictional properties of these contacts probably follow, something like a Rabinowitz style, weakening associated with the contact junction dimension. But it's the ensemble of all of them that is important in a slip weakening process and an earthquake nucleation process. And so that, then heating comes into play and lots of other things.
Georg, please.
In my simple mind, Massimo, I think D sub C in the slip weakening context is pretty well defined, right? I mean, it's a kind of displacement that you need in the process zone or in the cohesive zone to break down the strengths from the intact rock to whatever is residual, right? Now, in this context, I have a question, Chris. Great talk. So there is some evidence from experiments on analog materials, like, for example, from Simon Gerimacht and others, that with increasing load point velocity, increasing slip velocity, you actually reduce the nucleation patch size. So that seems to contradict be in contradiction to your observations. Would you have a comment on that?
Yeah, like I said, I mean, so, here are some measurements that show that D sub C increases as a function of velocity, but this is probably only in a case where you have some kind of dilation that occurs transiently as you start to increase velocity. I can certainly imagine cases where that won't happen. So I can picture cases where it could be exactly the opposite, which is what you're pointing out.
Mm-hmm. Okay, thank you.
Okay, Massimo.
I think just a short comment, Georg. I think that we need to discuss sooner or later in these days how much the experiments for intact rocks can be scaled and at which scale to an earthquake on a real fault. Gauge and strain localization of sheared material, how much they are, because this to me is the questions on comparing peanuts and apple.
Okay, maybe later.
Yeah.
Yeah, no, and I'm happy to switch into a different mode, although maybe Dan's got something he wants to raise here.
Yeah, so I just wanted to come back to this idea of, uniqueness, I guess, of this slip weakening distance. And, Stefan mentioned that temperature depends on velocity, for sure. It also, well, I mean, it really depends on the power that's produced, which is the shear stress multiplied by the velocity, and the temperature increase then is a function of the heat capacity of the rock. So I just think that, in experiments, in particularly high velocity ones, this might be obvious to everyone, I might be stating the obvious, but, we do very specific sets of experiments, really, where we control the displacement. And, the heat production then is a function not only of the velocity, but also of the shear resistance that you get too. So as that evolves, the amount of heat that you produce and therefore the strength, I talked, I guess, yesterday about these highly coupled processes, and I think the slip velocity, the strength, which are dependent on each other, and therefore DC are all very much linked. So I do wonder, sometimes whether we need to be thinking about doing different types of experiments, because for me the slip weakening distance will be totally strain path dependent, right? And I kind of quite like some of the experiments that I can think of that have been done in the past. So other people might be able to think of other ones, but Hiranoda did some nice experiments where he actually controlled the temperature on the slip surface during high velocity slip, and then have a look at things there. So it's a kind of a different way of digging down to the underlying physics of what's happening. And then the other one is Rek has obviously done some experiments where he controlled the power density as well onto the experiment too. And there are different boundary conditions to those experiments, which are giving us insight into the physics, because I don't think we can do a single experiment that will give us a definitive or unique slip weakening distance. That's always going to be dependent on the strain path that we choose.
Those are all really good points, Dan. Totally agree. I mean, but it reminds me also to say, you know, when you start to talk about thermal processes in an experiment where you're controlling the slip velocity, you can end up in a kind of a circular situation in a hurry, because if you're driving the slip and producing the heat, then when you get some weakening, it might not be something that would happen naturally at all, because you know, a natural process is one by which you got a stress drop that delivers enough energy to really make a weakening occur on its own, right? And to propagate a fracture. Whereas when you do a rotary experiment where you just increase the velocity, you can get all kinds of weakening associated with the energy that you're putting into the system, not the energy, you know, right? Not a spontaneous process. Okay, I feel like I should stop sharing my screen and turn things over to some of the contributed points that needed to be made. Elena.
Yes, I agree. In the meantime, in the chat, we have Casper asking one question. Is the dependence of D sub C with the thickness of the principal slip zone consistent with the existence of a critical strain? Maybe that was partly discussed. I don't know if someone wants to answer to this question.
Sorry, I didn't quite catch it. I guess I can read the chat. I didn't have it open.
Yeah, I can try to clarify maybe.
Oh, nice contribution. Yes,
yeah, so Chris, based on your presentation, I just had the thought that, okay, so you showed experiments of fault gouges which form continuous fault zones. And then you mentioned that the critical slip weakening distance depends on the thickness of these fault zones. And that clearly the critical slip distance, weakening distance is not a material parameter, therefore. But the question would then be, is critical strain maybe more of a material parameter?
Yeah, I like the idea of a critical strain. And then, geometry will matter in any of these systems that are granular. So, whether it's precisely a material property that's independent of everything, I don't know.
Yeah, okay, that's another question. Thanks.
Okay. So we have some contributing slide. One is the first one I got was from Alexis. So if you want to start sharing your slide and your contribution, you're more than welcome to do that.
Okay, one sec. Screen. Can you see the slides?
Yes.
Okay, so can you probably see this? Let me try and move that up way. Okay. Okay, so we just did some AE feedback controlled experiment, similar to the classic David Lochner experiments from the 90s. And we did it in a synchrotron, so we have a view of failure of the microscale process of damage localization and shear failure during one of these experiments. So I'm just going to play this video, and you'll see that this is a Clashak sandstone deformed at about 20 MPa conformal pressure. The development of initially tensile and echelon tensile cracks, mainly pore emanating, and then they start to rotate. So if you have a look, think around here, you'll see some of these cracks start to rotate to accommodate the grain fragments. So the grain fragments rotate, and then obviously the cracks either side rotate as well. So we see like a breakdown sequence of tensile microcracking, followed by fragmentation and rotation, accommodating the bulk shear motion, until we get to a point where the walls of the shear band are coherent and we get coherent sliding. So in here we've got tensile cracks accommodating dilation. We've got shear sliding on synthetically aligned cracks here, and also on antithetically aligned cracks as the grain fragments sort of rotate and then slide past each other. And then we have coherent slip. Excuse me. So we did the we also looked at the incremental strain fields, and this is the shear strain. I'm hoping they'll play at the same time. Yeah, here we go. The shear strain on the left and the dilation on the right, and we see a sort of localization of exploratory localization. So I'm just going to go back. I'll have to play one at a time, I think. Oh, sorry. Pause. Still going a bit mad. Okay, they're all going at the same time. So the dilation and the microcracking, we have an exploratory phase, and then it picks up on one side, and then the dilation goes across. So we have the tensile localization of tensile microcracking is like so the front of the propagating fault plane moving across, and then these sort of cataclastic mechanisms follow behind. And so what we looked at to look at the fracture energy was we took the bulk stress strain curve. We did just a normal sort of cubic fit on that, and we also took the stress strain at the CT scan times themselves. So if I go back here, you'll see that actually the CT scan times tended to happen actually as we were backing off the stress, which is why this curve is a little bit smaller, like the area is smaller under there. But then I also looked at the fracture energy on the shear band itself. So I took an object analysis of the shear band above a certain threshold. So this object, as it moves across the sample, at a threshold around here, which is where we started to see the tensile microcracks appearing, and then took an average of the dilation from the dilational field, and an average of the pure shear, local shear, so the frictional, so the microfracture and the frictional part, and then added them together. So this is the total observed local slip, which is quite a lot smaller. So the critical slip distance is a wee bit less than, so this would be the bulk measurement from the overall stress and strain if we didn't have any CT measurements. And here it's about 1.4, so a wee bit less. And then the energy underneath here is so 32% of this curve and 50% of this curve. So we actually see a lot less energy needed to break down intact rock in the shear zone than we might estimate from the bulk measurements. We also looked at the on-fault to off-fault strain. So there's about 12% of the total strain is dissipated off-fault. So we were inferring that maybe 12% of the shear fracture energy, of the fracture energy would be dissipated. And this is quite consistent with the UCL measurements. They did some velocity tomography and found a similar on-fault, off-fault strain ratio in granite. And so then we've got around sort of 20%, maybe 20 to 40% of this bulk bulk fracture energy not accounted for. And so the processes, the on-fault processes, I think going back to some of the discussions yesterday about the coexistence of many different processes all happening at the same time, including this sort of aseismic rotation of fragments, will can account for this discrepancy. And so I just took a few sort of back of the envelope calculation. I took a few cracks that we saw in the CT, and then I calculated the local slip as they rotated, and we could see that some of the cracks had as large as 77% of the total slip. So on average, if you think that there's a few cracks rotating, a lot of them are breaking up, there's some tensile cracks forming, then this mechanism could certainly explain some of the discrepancy there. I think that's everything that I've got. So I'm going to stop sharing, and we can discuss.
Oh, this kind of analysis is really promising. Very nice images. Thank you. Someone wants to comment on this contribution by Alexis? I have Zev on list.
Yes, a very nice experiment. I wonder if you could detect the location of the nucleation and the propagation directions from all the data. Because on the movie, it was a little bit difficult to do. Could you show this again? And
yeah, sure. You want me to? Let me find. Sorry, if I find my paper, I can show you a figure. 1 sec. Give me a chance.
in the acoustic emission experiments of Lochner, it was possible to pinpoint the location, the nucleation location.
Yeah.
And with your resolution, I think it's also ought to be possible. Did you?
So, yes, we did. Let me just show you this. Can you see here this picture? Let me try and zoom in a bit more. Okay, so okay, so this is the onset of strain. So we start to see here. Can you see this? My cursor moving around. Yeah. So we start to see some localization of so dilation is the blue and the pink, and shear strain is the green and the yellow. So we've got, so this is a pair, for example, at the yield point, and then we have this. So what happens is you get localization on these conjugate fault planes. I've actually got it in view of the plane. Let me show you down here. Yeah, okay. So you see these conjugate localized planes forming at around peak stress, and then you start to see it preferentially choose. So there's like two that it starts to focus on, and then this one starts to grow, and then you see the microcrack nucleation in this pink band here on this one side, which is associated with this pink area here. So this would be your nucleation patch, and then the pink propagates across. Well, it goes up actually a little bit, and then it starts to go across across the sample.
Okay.
And then as the shear strain, well, they're very, very strongly correlated, and the shear strain and the dilation kind of track across the sample, and then the slip obviously starts to take over, and you get just some asperities here that are breaking as the slip continues, and then very little dilation is happening during coherent sliding.
Okay, thank you.
That's brilliant, Alexis. Thank you. Stefano, do you have a quick question?
Congrats a lot for this presentation. I just wondered if you ever tried to do the same but with a soak up in the triaxial rock, just out of curiosity.
No, that's a really good idea. We haven't done that yet. We did a load of experiments on. We did a few experiments on intact Klashak and Berea sandstone. So this is the sort of the first results coming out of the experimental program. But yeah, saw cut is a really good idea, and we were actually also thinking maybe to do something similar, but with maybe not a saw cut, but a sample that was maybe damaged with the AE feedback. So you've got a more natural kind of emerged damage zone, and then try and slip that as well.
Thanks.
Okay, before listening to Omid, I would ask Federica to prepare the slides. Federica Paglialunga, she is in for the next contribution. And Omid, do you have a question?
Yeah, well, actually, my question was related to this energy budget and then radiated seismic energy. So we know the radiated seismic energy and the seismic efficiency is low, it's less than 1%. But I was wondering for this experiment, Alexis, that you did with this AE control, let's say, experiment, because in some ways when we do experiment, when we go with this, let's say, regular experiment, at the end, when we go to the dynamic or to the failure point, the fraction is dynamic. The system may saturate, a lot of superimposition of a lot of AEs may happen, and we are not really capable of taking the whole radiated seismic energy or calculated. I was just wondering if you have done calculation for the radiated seismic energy, and how was this experiment different from the traditional way of fracking the rocks?
So we didn't use the AEs to do the radiated energy. What I showed you was the strain field from digital volume correlation of the CT images. The AE location, the AE energy. So basically we had two sensors, top and bottom, that was all we had. And so we had, and we also had quite a noisy environment. So we had to have quite a high threshold in the synchrotron, because all of our cables went underneath the floor next to all their electronics. I mean, our cables were shielded, but there was still a lot of noise on the signal. We amplified it as much as we could close to the cell, but there was still quite a lot of ambient noise. So we definitely have an undersampling issue with our AE events, but they were enough to control the system. So we haven't done extensive analysis on the AEs. We've done a bit of analysis on the seismic aseismic partition, but haven't looked at the radiated energy. Yeah.
Okay, thank you. So I don't know, Elena, maybe I can continue later after this talk.
Okay. Sure. Federica, do you want to start your presentation?
Yes. Hello, everyone. So I'm happy to highlight our attempt to answer to this question: are fracture energy and vector work the same quantities or not? So what we did was to perform in the lab some rupture experiments, so analyzing the spontaneous propagation of rupture along the fault, and we used the analog material, so PMMA. The idea was quite simple. We wanted to compare two different approaches that have been used in the lab. So the first approach was trying to measure fracture energy in the framework of fracture mechanics, considering fracture energy, the energy consumed at the rupture tip in order to propagate the rupture. And we saw yesterday already with David Cameron and today with McLaskey how fracture mechanics is a very important tool capable of describing rupture dynamics. And so we did this on one side, trying to estimate fracture energies of our ruptures, getting values going from 1 to 15 joules per meter squared. And then we used another approach that was trying to compute the breakdown work as a collective dissipation term by computing the integral of the shear stress acting on the fault with slip through this equation that we saw already many times since the beginning of this workshop. And moreover, what we did, it was to compute another breakdown work, which we call the near tip breakdown work, which is the integral of the shear stress with slip, not until the final slip measured, but until a value that we estimated of DC. And so what we did, it was just to compare the values that the estimates of breakdown work and near tip breakdown work on one side and on fracture energy on the other side. And you can see in this bottom left figure that the values of fracture energy estimated through the fracture mechanics approach are quite similar to the near tip breakdown work that was measured using the slip weakening curve. So here on the bottom right, you can see the evolution of the total breakdown work, so the stars with the final slip and the near tip breakdown work with final slip, showing that the near tip breakdown work, very similar to the measured GC, is overall a constant quantity as expected from many studies that have been performed in the past, while the total breakdown work looks to be much more dependent on final slip. So from this work, it looked at fracture energy could be decoupled from the complete breakdown work. However, what we're working on right now is to study this kind of ruptures in light of recent contributions from Brenner and Bushbinder, and they try to describe the slip dependence of breakdown work through the occurrence of a non-conventional singularity order. So this was describing quite well what we were observing. In fact, if you can see here on the left, our evolution of the shear stress on the fault with slip. In our ruptures, we rarely reach a finite constant residual value of stress, and we rather have a continued, let's say, weakening, and this is reflected in the evolution of the breakdown work with slip. And this again could be explained by the occurrence of a singularity order that is different from the commonly known square root singularity, which is minus 0.5, and could be caused by frictional weakening that takes place in the wake of the crack tip. And so we try to use this theoretical prediction accounting for an unconventional singularity order, and they look to quite well describe our observed rupture. Of course, the occurrence of an unconventional singularity order would have a reflection on the interpretation of the fracture energy and of the slip dependence of breakdown work. And I will stop here.
I thank you, Federica. I think this is somehow related to what we have seen yesterday in some theoretical modeling we have seen. Massimo, do you have?
Federica, thank you very much. I really like the presentation, and I think that in general, what we are discussing during these days is the partitioning of the breakdown work. Now, the identification of the terms of this partitioning, in your case, you identified one part of the breakdown work is the fracture energy, scale independent, and another part, it is, let's say, the slip dependent work, which both compose the total integral below the slip weakening curve. But this strongly depends on the shape of the slip weakening curve, because in this case, you have a very sharp drop associated with a curvature that is a long tailing decrease. So in high velocity friction experiments that Stefan showed before, this can be also explained by flash sheeting plus others. So in general, do you think that the partitioning of the breakdown work can be generalized? So for this set of experiments with PMBA, with this material is one type of interpretation, but I think that one of the ideas is to try to generalize the way in which we can perform a partitioning of the breakdown work and perhaps identify what we call scale independent fracture energy.
Yes, yes, I completely agree. I'm sure that the same reasoning could be done, of course, with drugs. Yeah, I like the idea. It's a bit a more philosophical comment, but of a scale-dependent critical distance, depending on the kind of frictional or thermal weakenings that are being activated on the fault. Yeah.
Because one of the things that interests me is that in general, which is how we can identify this switch distance that here you have identified with this subsea. So in some cases, if you have flash heating with others, it is dependent on the scale. So you switch from an asperity scale mechanism to a bulk mechanism. So do you have here an interpretation, a physical interpretation of this subsea that you identify for partitioning the breakdown work?
So in this specific case, this subsea was estimated. With the fracture mechanics approach, used linear elastic fracture mechanics and the cohesive zone model. And so, the cohesive zone model outputs a value of for the cohesive zone. And so this cohesive zone can be translated, let's say, into a critical slip distance. That's how we estimated this this distance here. So it should be referred to the rupture front.
Thank you.
Very nice. We have two raised hand from Stefan.
Yeah, sorry, I just
you are really motivated.
I logged in twice because my computer crashes sometimes, so I have a backup one. So I raised two hands. So first, I have a remark for very nice work, Francesca, and I think what I think is interesting is that GC here, if it were to remain constant, it would rapidly become negligible in an earthquake. So should we even worry about that? Because the WUBI increases, the breakdown work, the slip-dependent breakdown work. Here it is measured on amount of slip, which is, I think, 4 microns or a few microns. So if really GC remains constant and in earthquakes you have slip of several meters, then it will become rapidly negligible, right? And we would only worry about the breakdown work, which happens on a scale of a few centimeters or a few decimeters of slip or more, but it would be small enough probably that it would still concern a very small portion of the rupture, which we could still define as a zone close to the crack tip in relative terms, of course, because the scaling would be different. So that's the first remark. The second remark is that I think the energy flow, which is the counterpart of the critical fracture energy, usually scales with the length of the crack. And I was wondering if you measured your GC for different crack lengths or at different distances from the crack nucleations, rather than with final slip, which may be related to other things like the control of the, edge effects of the samples or something like that.
So I will start by this last question. So the final slip that you see here in these plots is referred to the same location at which the fracture energy is estimated. So it's not the macroscopic slip of the block, but it's really the final slip of the rupture at that specific location. And yes, I did compute the fracture energy along the fault, trying to, yeah, but I didn't find any clear dependence on the crack length. And for the first question, yes, that's what we thought at first, but so this second part, I don't know, maybe it's a bit more, I don't know, interesting or complicated at the same time. So this shows, this work of Brenner and Bushbinder shows how frictional weakening or continuous weakening behind the crack tip can influence the singularity order. So in that case, if that happens, it means that the rupture dynamics are controlled not only by the near tip dissipation, but also are controlled by the long tail dissipation. So for dissipation occurring in the wake of the crack, and that can make, of course, the fracture energy not negligible anymore, because then the breakdown work would become slip dependent, and the dynamic of the rupture would still be affected by it.
Thank you.
I'll just chime in to say that we have several other people who want to make a presentation right today. Maybe some of them could go tomorrow.
This is exactly what I wanted to say. I know that Francois is available to move his presentation to tomorrow. I was chatting with him now. Okay. We have Feinberg, Dresen in list still, yes. So I don't know, I would ask this presenter if you want to contribute now.
Well, I think we should, as for me, I would prefer to continue the discussion. I can show my slides tomorrow, it's only 2.
Fine. We can go another 15, 20 minutes. I know that Massimo Cucco has a hard deadline in about 20 minutes. So anyway.
Yes.
Personally, I don't care either. I may forget what I want to say by tomorrow, but it might be much more interesting anyway.
No, maybe you can share your slides now if you want.
Okay, I mean, whatever you prefer.
In the meantime, I see that there is a question by Dimitri, David, Georg, and Greg. So maybe we can continue this discussion, then see if we have some time also to see.
I would much prefer that.
Okay. So let's go. The first in line is Dimitri.
Well, it's concerning the Frederica's talk, which was great. Thanks, Frederica. And I think the comment by Massimo, whether they're in fact, I guess, different processes, perhaps the first one that can be identified with this with the low value of this C, and then the continuing weakening process after. I was just wondering, so the question, I guess, to Federica from this perspective. So I guess you have tried to vary the normal stress and therefore to suppress to an extent by decreasing the normal stress, suppress the continuing weakening, and therefore isolate the first process if they are indeed different. Perhaps there may be a similar way or an alternative way is to basically run the smaller slip ruptures at smaller stress. So basically looking at this cutoff stress at which you could run the smallest slip rupture, and that, I guess, by definition would only be driven by that first process with small d-sub-c. So I don't know what you think of that.
Yes, yeah, that's a good idea. I tried different applied normal stresses, and but I didn't notice a very big difference in the behavior. So I might try to lower the normal stress even more, just to see how that affects the weakening curve. Yeah.
Well, I guess I meant maybe not normal stress, but the stress ratio, so the shear to normal stress. So at some point, if you apply too low of a pre-stress, you won't get, I guess, any rupture.
Yeah.
But just large and pre-stress, just large enough to get a rupture, maybe a pulse instead of a crack, that would have a slip on the scale of your lowest disapsy value, and then that might be approved by action that there is that single mechanism, that you can isolate that mechanism.
Yeah, I'm not sure it will be easy to try because that's like spontaneous rupture nucleation. So like as soon as you reach the critical stress, it just propagates. But yes, maybe controlling the normal stress will also affect that. I will try. Thank you.
David?
Yes. Thank you, Federica, for a very nice contribution. I actually don't have a question. I just wanted to make a statement that I'm in support of this. I think is very clear, follows the sort of the definition that I tried to push yesterday. It shows nicely the difference between what would be the fracture energy that you define as the tip, and show that it is the fracture energy. And I think that is very nice work. And I think it also shows, to refer to the question that I think Stefan had before, and you stated nicely, I think, that the fracture energy should really not depend on the crack length. But if you look at that breakdown work, this is why it's so important to distinguish between the two. The breakdown work might depend on the crack length. But it might not be the fracture energy which governs the rupture. And I think what you showed actually is the basis to demonstrate that. And hopefully we could show that also that this is the case. The fracture energy is constant and the breakdown energy maybe depends on the position and is the one that maybe is measured in other experiments, but not the fracture energy. So just to say, I think it's very nice work and it really points in a very good direction.
Thank you. Yes, indeed, I will try. I didn't focus much on looking at the dependence of the breakdown work with the crack length, but yeah, I will look more in that direction. I'm sure there will be some kind of dependence. Yeah.
Yeah, Marco.
Yeah, Federica, great talk again after EGU. So I'm very much also in support of this, dualistic nature of the process that you have a rupture front propagating through your material. Now we've been observing that in all sorts of materials, from claystone, sandstone, granite, etc. The difference is that in contrast to these PMMA experiments, we have rough surfaces with distinguished disparities. And then the picture becomes really complex because it's very difficult to sort of monitor the propagation of a single rupture front. It could be that you have ruptures that initiated different disparities almost contemporaneously and then migrate towards each other and so on. With regard to the remark of David and also Stefan, I would just try to draw your attention to the work of Chris Scholz that he started in the early 90s, where they looked at process zone in the field, and they found that the slip or the displacement length profiles of the faults that they were investigating were more or less scale invariant, and that the process zone was in fact increasing. So what you are arguing is that the fracture energy would be constant if there is not a mechanism that increases the toughness for some reason. So Onaka has suggested that there is potential mechanism because you may sample a larger volume and thereby you have, you run into a specific distribution of defects that are, have a length distribution that's power law distributed, as was shown by Ian May a long time ago, that define the size of the potential asperities that you run into. So I think, and thereby, define the strength of the fault as it grows. So I would just like to emphasize that there is this this idea that the process zone might actually increase with progressive lengths of a fault. And I mean, there's plenty of evidence from field observations that seem to show that.
Okay, thanks. Federica, were you saying something?
No, I was just thanking for this comment. Yeah, it's a good point.
Next in line is Jay. So I don't know if Jay, do you want to also take the chance to present your contribution at this point?
Well, I just raised my hand, so I wouldn't have to, but whatever you want. I just wanted to ask Frederica a question, whether she's sure that only a single rupture front was running through the material when she was doing her measurements, because you often have, as was mentioned, numerous rupture fronts, one after another, which could give a similar effect.
Yes, yes, I would say I'm sure. So we checked, we had the accelerometers on the fault as well, and the strain gauges were checked with the accelerometers, and we made sure that we considered only the very first time window until until the slip reached the kind of plateau, and we discarded all the rest. So I hope that is the case.
Okay, thanks.
Okay. Jay, would you like to present your contribution? Maybe Stefan, if we have time, we can move your question to the end so we can, as a conclusive remark. Do you agree? Okay.
Okay, good. So can you see my presentation?
Yes.
Okay, now I just have to find the right button to push to turn it on or something. Well, we'll do it this way. Okay, I'm going to be, since I have to be fast, I'm going to be very blunt. So I want to show a simple experiment that we did a few years ago. This was an experiment done by Ilya Svetlitsky, where we checked the equation of motion for a shear crack. But the first thing I want to show is this thing, which is, this is the shear stress we applied to the sample before any rupture took place. And each one of these lines was for exactly the same normal stress imposed, or normal force imposed. So immediately you see here that there's no characteristic friction coefficients, because you can store either a lot of stress here or a little bit of stress here for the same two blocks. The only difference here was we artificially nucleated the rupture earlier here, whereas here we allowed the material to increase its stress before, again, artificially nucleating a rupture. And the result of all of this stuff is basically, it's very different dynamics. So you have initial stress that's very low, then you're going to get very slow rupture fronts, actually moving at a small percentage of the Rayleigh wave speed. Whereas this guy, where you've stressed the material by a lot, you move very rapidly, you accelerate to nearly the Rayleigh wave speed of the material. Now, all these look kind of strange, but if we use fracture mechanics, basically as David explained yesterday, without going into any details, we can collapse all of these data to a single curve, which is shown here. So the equation of motion for a shear crack, LEFM, basically describes all of this stuff. And the point being is that we don't need any friction law at all. Basically, if we throw out our preconceptions that we've been brought up from kindergarten with, that you need to have a critical stress in order to have something to move, a friction law, and just allow the fact that a given system can store different amounts of potential energy or elastic energy before nucleation, you get earthquakes, and they're very well described, both their dynamics and their arrest. So we can play with the stress profile. And in this paper here, we've shown that we can predict at least in the laboratory in earthquakes, magnitude, again, no friction law at all. Again, this is what I was saying. We have a range of overstresses here, basically showing that a characteristic friction coefficient doesn't exist at all. It doesn't. You don't need it. So you can talk about rapid velocity weakening as a way to explain this, but you don't really need it. People are attracted by friction laws basically because if you have, for example, velocity weakening, friction law, one size fits all, you can get earthquake and ruptures and all this stuff. You really don't need it. In fact, under these conditions, you can have strongly velocity strengthening friction and still see the same kinds of rapid ruptures. So you just need fracture mechanics and the ability of the system to store to store varying degrees of potential energy. Now, what determines the energy budget? So just following Abercrombie and Rice, the introduction, which was beautiful, the total energy, the total elastic energy change is given by the seismic radiation, the fracture energy times the area of the fracture, plus a contribution due to friction. So let me first say that fracture mechanics deals with the first and third parts. So it describes quantitatively very well the seismic radiation, at least for a simple crack, and the fracture energy. Now, where is this frictional dissipation? That's basically, as Dave said yesterday, okay, at the crack tip, we have what I define as the fracture energy. So it's just the amount of energy we need to create, to deform, break, or whatever things near the crack tip. And behind that, that's where friction plays a role. So we've, in order to map this problem to fracture mechanics, we basically subtract away the friction law. And if it's more or less constant, we can do that. For example, rate and state, the velocity contributions are on the order of 1% from the mean, so that's fine. And then from the slip itself, after the fact, we can calculate how much frictional dissipation, where by friction I mean the resistance along the actual surface to slip, how much that contributed. So just to summarize, fracture mechanics can actually talks about fracture energy and the seismic energy. It also can play a role in estimating the frictional dissipation because it tells you what the slip profile is going to be. If anyone's interested, I can tell you how to get this hand-waving expression, but this is the fracture energy that plays a role here. As I mentioned earlier, the D sub C that we see in experiments is microscopic, but the fracture energy is much smaller than this, than the residual energy here due to frictional sliding. On the other hand, it's the fracture energy and the stress within the sample that before a rupture that's what controls an earthquake. The slip and whatever processes take place back here take place at regions where the fracture, the earthquake, the leading edge of the earthquake is already kilometers away. So the slip, the frictional resistance here cannot actually influence what's going on here. So that's basically what I wanted to say. I hope I didn't get anybody upset, but I tried to be fast and furious, and I've already had enough to drink, so thanks.
Thanks. Let's see what the community is thinking. Stefan is the first in line. He was also waiting on before, so.
Yes. No, this is exactly the same question as I wanted to ask before. Now, because Jay has shown this, I think the question is addressed to him directly. So I agree. So with the fact that fracture energy, or at least the fracture energy, not the energy flow, but the fracture energy of the material comes from the damage in this region close to the crack tip, which you call CF here, I think. And you say this is near tip damage. So my question is, how near does it need to be? And is it as near in a 1 millimeter crack in the lab as it would be in a 1 kilometer earthquake fault?
Well, that's the billion-dollar question.
How small is this plaque tip region? Is it always the same size? If it grows, is not fracture energy go to grow proportionally to the size of this plastic region?
Okay, a wonderful question. I even have an answer, which is the definition of a wonderful question. And my answer is I have no idea. But what I can say is that all of this phenomenology works so long as the relevant energy being dissipated is in a small localized region compared to the 1,000 by 1,000 kilometer plate or whatever that's being stressed. So if we have a singular field that's driving this process, the size of the process zone, cohesive zone, whatever, could be 100 meters, it could be a micron. And all of this will still work. The numbers will change, of course. What drives an earthquake is the ratio between the static energy release rate, or the amount of energy stored in the system, and the fracture energy. But whatever the value of the fracture energy, the scale at which the fracture energy takes place, it doesn't influence this picture. Now, people have mentioned a lot of different scenarios where the cohesive zone surrounding the crack tip could be huge. You know, Pablo yesterday talked about Andrew's picture where he just assumed a linear increase of the plastic zone. Okay, still fracture mechanics takes place, and we still need to understand the damage mechanisms involved. Is the crack tip really defined by a micron scale? In an earthquake, probably not. What defines D sub C? I'm going to say something very stupid, but I'm allowed because I'm a physicist. If I look at, for example, the Tohoku earthquake, which I probably pronounced it incorrectly, but you know, go with me. Basically, we had a magnitude 9 earthquake because the earthquake slipped from one big asperity, it overcame it to another big asperity and got stuck. So in that case, one might see the D sub C instead of a micron as the size, as the distances between two barriers, where the earthquake, the traditional earthquake in that area at magnitude 7 or 8 got stuck on one barrier, and it got past it and got stuck on the next one. I think we have to look at earthquakes in this sense as hopping from one. I mean, it's not my idea. A lot of people talk about heterogeneity controlling earthquakes, and I think any variation of this quantity, the fracture energy, by whatever means, will determine what an earthquake's length could be. It's not necessarily the stresses involved. So I don't know if I answered anything, but yeah. I ran over there.
Yeah, that I basically agree with you, Jay, except that for the energy flux, which I think the slide is still on, G, the energy flux, yeah, that will be proportional to the stress drop. Do you agree with that?
Would it be proportional to the stress drop? It'll scale somehow with the local stress drop.
Okay.
But what the maximum stress is, it depends on the material.
But then, in that case, the stress drop is controlled by friction. So I don't think we can throw friction.
Not at all. Why should the stress drop be controlled by friction at all? I can break this piece of paper without friction. I make a little crack in there. And look, I have a rupture. I did that fast, so I'm not sure if my camera caught it.
That's stress concentration, but there's no
friction in this problem. So there's no
But Jay, if you want to
law
have
that I
more than
need.
That's a
one,
mode 1, Jay.
yeah, you gotta, if you want to have
but
more
I
than
can
one
map
effect,
again
you
mode
gotta-
2 to mode 1. It's
Then
the
you
gotta
get
same
build it
problem.
back up, right?
Okay, but anyway, that's all I'm saying, that we don't need a friction law to create either a stress drop or fracture energy, or an earthquake for that matter. It might be plausible to use one, but it's not necessary.
If you want to have more than one rupture on a fault, Jay, you got to have some way to regain strength. So if you want to call that a friction law, you can, or if you have to invent the strength again, right?
Well, yeah, we get healing. That's fine.
But that's what a friction law does for you. It tells you about how
No,
to heal it.
the friction law as it's generally used is used a lot more than that. You use the friction law to produce, for example, velocity weakening. And the lore is that you need velocity weakening, for example, to create an earthquake. You need to create an instability. That's not really true. All you need is more energy in the beginning than you have in the end. You don't need the friction law to provide that.
If you want to have more than one rupture, you've got to have healing. Otherwise, you're only going to get one.
Sure, but it doesn't necessarily, it's not necessarily the same as the friction law. There is healing, obviously, and you have healing that's logarithmic in time, even in my experiments. But you don't need the friction law to give you this drop in stress at the tip. It's really not necessary.
Oh, no, let's have a couple of the people get their point in, and then 8 minutes, and we're gonna quit. We're seriously over time.
Yes, exactly. Next in line was Bin Hao. I'm sorry if I mispronounced your name.
Yeah, it's my name is Bin Hao. Thank you very much. Great talk, Jay. I was also thinking of this kind of picture, combining friction and fracture. I feel this totally makes sense to me, but the question I want to ask is how can we prove that this picture is the truth? How can we prove that this works? Are there any differences provided by the predictions from this model versus the prediction by a pure friction or fracture point of view?
I can measure everything in the laboratory in these experiments. I mean, I can't do it on a natural fault. Don't know how to get down 15 kilometers or something with a strain gauge. But everything here, it's not hand waving. Okay, I'm waving my hands, I understand. But it's entirely quantitative. There are real numbers here. I can measure the fracture energy. I can measure the stress distribution along a fault in the laboratory, and I can predict exactly how long a rupture is going to be, how fast it's going to be. You know, all of this stuff. You know, I take what appears to be random distributions of shear stresses, and I can collapse them on a single curve. I mean, how much more proof do you need that this stuff works? And again, you don't need a friction law for this. It has nothing to do with friction. The only thing that I need from friction is for it to be roughly constant, so I can subtract it away and create an essentially a mode 1 problem, or mode 2 for shear fracture. That's all you need. I guess I've had too much to drink, so I've become overly passionate, but okay.
Okay, thank you.
Can I ask Dimitri to go ahead?
Thanks, Jay, for being overly passionate. It's very, I'm very sympathetic. I think the key thing that you mentioned, what you need for this picture to hold, is for friction behind the front to be approximately constant, or being approximated by constant, which means that in this particular experimental setup, you don't have what we refer to here as continued weakening with event slip. And maybe it's a result of the fact that
it exists here. In fact, you can fit rate and state friction to plexiglass and its velocity weakening and all that. But the changes due to the log V term are on the order of a few percent. So it's basic, so I can still subtract it away and I sleep well at night. What Frederica talked about, for example, if you have a strong dependence on the tail, if such a thing exists, then fracture mechanics still holds, but it changes. That's what these funny exponents or funny powers that she was talking about, anomalous powers, that's where they come in.
Yeah, I guess I was going to make a comment that, let's say, we know that there's, or at least from theoretical models, that these continuum weakening processes, they arise due to shear heating and related, thermal pressurization, flash heating, etc. So it just happens so that in your experiment, maybe because of the low level of normal stress, that you don't have a signature of those processes.
I see flash heating in these. It's not true. There is flash heating here.
I'll finish in 20 seconds.
Okay. Sorry.
But perhaps, so basically, it doesn't mean that they don't exist. And so if friction keeps weakening in the tail of the rupture, then this argument no longer works. So maybe the dissipation now is not just localized at the tip, it's smeared over entire fracture, but nevertheless, it influences the energy balance, and therefore it influences how the front propagates. I guess that's my point.
No, it's not. Okay. Basically, the tail of the crack doesn't influence the head. And why is that? Because it takes a long time for first of all, we see flash heating at the tip. We've done experiments where we can see that. It happens, and certainly in plastics, it melts. But by the time you have, for example, along a rock gouge formation or comminution or whatever they call that stuff, you need enough slip. You need a sufficient amount of slip in order to get shear localization or whatever. By that time, the tip of the earthquake is a kilometer away. Certainly, all of these processes are important when you want to calculate the energy budget, but they're not important, I don't think, for controlling the earthquake itself. The earthquake itself, for me, is the rupture front. So the rupture front is not influenced at all by processes that are relatively slow. Even when you see in the rotary shear experiments rapid decreases of the friction coefficient with the velocity, you still have to run them a fairly long time in order for those decreases to happen. Once you've done that, the crack tip again is very far away from where all these processes are taking place. I'm not saying that they don't take place, but all I'm saying is, at least nearby the crack, if I can approximate the friction as more or less constant, that's all I need. If something else happens along the tail, we can deal with that, but that's not the point of what I'm trying to say.
Are you trying to say that the rupture front would run too fast for the dissipation in the tail to be delivered by the waves to affect?
Exactly. It's moving near the shear wave speed, and the speed of information is about the shear wave speed. So you can't.
In a nice plexiglass experiment.
Can I ask you to move this conversation to maybe tomorrow or later time, because it's 7 o'clock. This is very interesting that it has to.
That's exactly the kind of problem we want, is to have too much interest. So everyone who's still got their hand raised, 1 minute, and then we're done. How about?
Okay, it's Georg. You're muted.
So I guess my question goes in the same direction as Dimitri. So you don't think, Jay, that if you have maybe a little bit more complex scenarios than in your experimental setup, where you have asperities and the rupture, as you sort of suggested, jumps from one asperity to another, across that surface, and maybe in one asperity you have a rupture going through, and the other asperity the rupture has already gone through and friction takes place, you don't think that affects each other's?
It happens too quickly.
Yeah.
In other words, if you have heterogeneity in the fracture energy, you can actually stop a sonic rupture, even a super shear rupture on its nose. But that's because these variations or the heterogeneity is ahead of the crack. Behind the crack, since the information about the friction law or the frictional resistance has to reach the crack tip, and the speeds at which it happens are sound speeds, more or less. And since the crack is moving at approximately the sound speeds, that information won't get there. I mean, I can show you to you mathematically. Ben Friend did it, he wrote a whole book about it, what the effect is of putting different tractions on the crack faces, how long it takes for the effects of the tractions to reach the crack tip. It's not mine, luckily, so that means it's correct, probably. But
well, you're always thinking about one singular front, right? Not something that is sort of distributed across the surface.
Sure, but each one, I think, is, the chance that you can excite more than one front at a given time is probably pretty small.
Well, I can show you tomorrow on the slide that is actually what is often happening in experiments.
Okay, well, in our experiments, we see numerous rupture fronts running back and forth, but they're always very polite. It's one at a time. And we also get aging of the surface, and that allows, actually, that's why you get generally super shear rupture fronts that are moving like as an aftershock or something like that often, because the fracture energy is very low because the surface hasn't had a chance to heal. So the stress drop is very low, but the fracture energy is even lower. So if you want, if everybody still has patience, I can show pictures and all this stuff, but I was told I get 2 slides, so whatever.
I would suggest to move this discussion up tomorrow, because in any case, we will wrap up all this contribution. There is Vito who has his rise, and then we will close, I suggest.
Yes, just as a remark, so in the second slide, Jay, so we're showing that friction plays a role just as in the residual strength in the tail of the rupture. But really, what happens at the rupture tip in like how the shear strength increases and how it decreases and over which length scales depends on, in fact, on the nature of friction, because it doesn't just depend on the material, because for the same material under different conditions, there can be a larger or smaller initial increase in the shear strength and over various length scales, and that affects the fracture energy. So friction plays a role even in this crucial part, not just in the tail of the rupture.
Well, I agree to some extent. I mean, we had this discussion a few weeks ago or something, but the stress drop, okay, the bottom part, the peak stress or whatever, that's the material strength. And it will drop to some value of a residual stress that could be affected, for example, by numerous processes, from melting up to the release of gas or something like that. So that the stress drop at the crack tip could be, certainly that influences the fracture energy. It also influences, if it happens fast enough, the crack. Now, then it becomes a philosophical question though, is this a friction law or not? Is this, because it has to happen fast enough. So if it happened, call it your pet dog or something. If it happens within a microsecond or something, it is relevant. If it takes an hour and a half to drop, it's not relevant. In the middle, we can discuss, but so maybe maybe my terminology isn't what people want. Friction law. So we then, just like we have to define what D sub C is, we also probably have to define what we actually mean by a friction law. So the material characteristics around the crack tip are important. If you want to call that a friction law, fine. Okay, I'm happy with that. It's words. But so I think I agree with you somewhat to end this evening on a happy note.
A lot of great things to think about for tomorrow. Elena, fabulous job. Yeah, really interesting. So
running fast, very fast.
we're going to meet again tomorrow, and we have a fair bit of time. There's a few people we should apologize to. Sergio Vinciguerre was going to present something today. Also, Georg. I don't know who else I'm forgetting.
François and Georg.
Okay,
so
hopefully you don't mind to present tomorrow. I think
no problem.
Thank you.
Great discussion, everybody.
Thank you. Ciao.
So for tomorrow as well.